So, in our last lecture, we have seen Rouche's theorem that is providing the locations of zeros, of an analytic function. Okay. So, in this lecture, we are interested to do some applications of Rouche's theorem as well as open mapping theorem. Okay, and the proof of open mapping theorem is based on Rouche's theorem, but that theorem is itself an important theorem. Okay, so the first thing that I am going to take is that the proof of fundamental theorem of algebra that we can get from the Rouche's theorem. That is the fundamental theorem of algebra that we all know. Of algebra. Okay, so which is saying that every non-constant polynomial with complex coefficients has at least one zero, that has at least one zero in C, and in fact and hence has exactly n zeros, n zeros in C. Okay. So, this is the fundamental theorem of algebra, and we all know its proof by using Liouville's theorem. Okay. Now, we are trying to give its proof by using the Rouche's theorem. Okay. Now, to prove this one, I am just taking let there is a non-constant polynomial, let there is a function, there is fz, it is the a naught plus of a1z plus up to a of n minus 1, z of n minus 1 plus of z of n. Okay. So, it is a polynomial of degree n, that is one thing, where all these coefficients, that is the all of ai belongs to C, where I is equal to 1 up to n minus 1. Okay. Further, I am taking and let C be a circle of radius r. I am just taking this is a circle of radius r with the conditions that r is greater than 1. Okay. Then for z belongs to C, if we take z which belongs to C, we have it is the just we are taking fz upon z of n minus 1. So, simply we can see this is just a naught divided by z of n plus of a1, it is divided by z of n minus 1 plus up to it is the a of n minus 1, it is divided by z. Okay. So, this is the we are getting this one by this one, this is the using triangle inequality, we are getting this is the a naught and mod z of n, where mod of z is the r. So, it is just the r of n plus it is mod of a1, that is the r of n minus 1 plus up to it is the mod of a n minus 1 that is divided by r. Okay. Now, we have that this r, this number r is greater than 1. Okay. So, therefore, we can write that this is the modulus of a naught plus of a1 plus this is up to a of n minus 1 and that is divided by r. Okay. Now, if we take a R, if we take R is a large number, therefore, thus for a large R, that is, if we take R is a number which is greater than the maximum of 1 and the number A naught, modulus of A naught, it is the mod of A1, and that is up to a mod of a n minus 1. Okay, if this is, then we have that is the f of z divided by z of n minus 1. This modulus we are getting that is less than 1. Okay, so by this one we are getting this is the mod of fz minus z of n that is less than z of n. Okay, now if we take g, let there is a function g z is equal to z of n. Okay, so this last inequality it gives that this is the fz minus it is the g of z that is less than of gz. Okay, now by using Rouche's theorem, the number of zeros of f in C will be same as a number of zeros of g in C. Okay, and we can see this function g, this is having 0 at z is equal to 0 of order n. It means this n of g is a n. That means the n of f, the polynomial that we have taken, that is having the n root in R, that is having n root in mod z is equal to R, where R is a sufficiently large number. Okay, so by this one we have obtained that a non-constant polynomial of degree n is having exactly n0 in complex plane C. Okay, so therefore, by using Rouche's theorem, we can get the proof of fundamental theorem of algebra. Okay, now we are interested to do one more applications of Rouche's theorem, that is the open mapping theorem, which itself a very important result, which is saying that this is the open mapping theorem. So, what the open mapping theorem is saying that if f is a non-constant analytic function on an open set D, then this f is an open mapping. Then we say this f is an open mapping. Okay, so we are saying that f is open mapping. We can also say that is this fd, that is the image of D under f is an open set. Okay, so the open mapping theorem is just saying that if f is a non-constant analytic functions in an open set D, then the image of D under f will always an open set. Okay, so this is the open mapping theorem. We will do the proof of this open mapping theorem, but before this one, we are interested to see that we can also have a generalization of this result. Okay, so we can have the generalization of this open mapping theorem in which we can replace this open set to a domain. So that is we can also have a result that is the if D is a domain, this is a domain, that is a domain in C, and F, and we are having F is analytic in D, that is analytic in D, then FD, then FD, that is the image of D under F, is either a domain or a single point. Okay. Therefore, if f is a non-constant analytic functions in a domain D, then FD should be a domain. If it is not a domain, then it should be a single point. Okay. So before proving this open mapping theorem, we are interested to do one applications of open mapping theorem, that this open mapping theorem simplifies some general problems in complex analysis. That is, I am just taking a problem that is let F be analytic in a domain D, and if mode of F is constant in D, this is constant in D. Okay, then F, this F is constant. This should be constant. Okay, so this is the problem, and we are interested to see the solutions of this problem by open mapping theorem. Okay, but before this, we can see that we can also prove this one by using Cauchy-Riemann equation. Okay, that is the if we use the Cauchy-Riemann equations, that is if we take Fz, let Fz is equal to u plus iv, we have taken, then the mode of F is equal to C. So this is just the this is equal to u square plus v square is equal to C. Okay. Now if we differentiate, this is the C square. Now if we differentiate this with respect to x and y, so we are getting this is the u of ux plus it is the v of vx, this is equal to 0. Also we are, if we differentiate this equation with respect to y, so we are getting this is the u of uy plus it is the v of vy, this is equal to 0. Okay. Also it is given that f is analytic in domain D. So if f is analytic in domain D, it means f should satisfy the Cauchy-Riemann equation. That is the Cauchy-Riemann equations that are this ux of xy, this is the v of y, this is the x of y, also this is the uy of x of y, it is the minus of vx of x of y. Okay, so since f is analytic, so it should satisfy these CR equations. Now using these CR equations, in these two equations we may get the equation, that is the first equation I am writing as it is. This is the u of ux, it is the v of vx, it is 0. And in the second equations I am using CR equations. So I am getting this is the minus of u of vx plus of v of ux, this is equal to 0. Okay. Now if I multiply this first equations with u and the second equations with v, and if we add these two equations, so finally I am getting that u square plus v square of ux is equal to 0. Okay, and as we know, as we have that this u square plus v square is c, so this u square plus c square is not equal to 0. Okay, here we should take this c is any number, this is not equal to 0. So if c is not equal to 0, it means we are getting that this ux this is equal to 0. Okay, So if this ux is equal to 0, we have obtained this ux is equal to 0. So similarly, we can obtain by using the CR equations that uy is equal to 0. And again, if we use the CR equations, that we can obtain that Vx is equal to 0 and Vy is equal to 0. So finally, we are getting that if we have the derivative of f, so this is just the ux plus iota of Vx, and by using these equations, we are getting this is equal to 0. Okay, now we can write this is the f of z minus f of 0. This one, this is just the integration, this is the 0 to z, this is f prime, and that is some zeta of d zeta, and we know that this f prime zeta, this is equal to 0. This is equal to 0 in domain D. So if this is equal to 0, so finally this integration will be 0. And if this integration will 0, then we are getting that fz, the value of f, this is the f of z, this will be the f of 0. Okay, so that we are getting that f is constant. Okay, so we can have the solutions of these problems by using the Cauchy-Riemann equations, but we can see that it is having little calculations. Now we can see that by using open mapping theorem, we directly get a conclusions that f should be constant, because we are given that if this is in the z plane, this is the given domain D, okay, and we are given that f is analytic in domain D. Okay, so by the open mapping theorem, if f is non-constant, then f of D should be a domain, because here D is a domain. But we are given that this mod of f is equal to C. So the mod of f is equal to C, it means this is the if w is equal to fz, and if we are having it is the w plane, so mod of f is equal to C, it means mod of w is equal to C. So we are getting a circle of radius C. This is the mod of w is equal to C in w plane. Okay, so therefore this mod of fz is equal to C. This is a circle which is the image of this domain under this function f. So if the open mapping theorem holds, then the image domain should be an open set. But we can see that this image, this is the image set, is not an open set. That is, we see that this is, if we take this w such that w is equal to C, it is just a circle. So this is not an open set. And not an open set. And if this is not an open set, it means the function then by the open mapping theorem, this f should be a constant. This f should be constant by open mapping theorem. Okay. So we can simplify some of the problems by using the open mapping theorem. Okay. Now we are going to prove this open mapping theorem, and to prove the open mapping theorem, we will use Rouche's theorem. So to prove the open mapping theorem, so we are giving the proof of this open mapping theorem. So we just first we take, let f be non-constant analytic function in D. Okay, then to prove our result, then to prove our result, we need to prove that we need to prove that this we need to prove that every point point A of f d, this should be an interior point. Okay, is an interior point. This is an interior point. Okay, that we need to prove. Okay, now to prove this one, I am just taking let gz be a function such that it is the fz minus fa. So we have taken this A is a point in the image of D under F. So further we are taking gz is equal to fz minus fa. Okay, and we can see this g, this g that has 0 at z is equal to a. Okay, also we know that the zeros are isolated. We already proved that the zeros are isolated. So this 0 z is equal to a should be isolated. If it is a isolated 0, it means the neighborhood of a will not have any other 0 of g. Therefore we say that there exists a disk delta of AR, and that is a disk at center A of radius R, this one, with the property that its closure, that is the delta bar A of R, it is contained in D. Okay, such that since the 0 of z is equal to a is a 0 of g and the zeros are isolated, so we can write this fz minus fa. This is not equal to 0 in the dilated neighborhood of a. If we take the dilated neighborhood of a, so in that dilated neighborhood, this fz minus fa will not be equal to 0. Okay. Further, I am taking this let C be a that is the circle at point A of radius rho. That is this is the z such that z minus a of this is a mod of z minus a is equal to rho. Okay, where we are taking this rho is in between 0 to r. So we can see this rho. For every rho, we are getting the concentric circle at center A of radius rho. So all these circles lie in this disk. Okay. So that means therefore we can write then for zeta, if we take zeta is a point on C, this is a point on C, we have f zeta minus f a. This is not equal to 0 because this zeta is a point on a concentric circle at a point A of radius rho, where rho is in between 0 to r. It means this zeta is a point in the disk of radius r at point A. So this f zeta minus fa is not equal to 0. So if this is a non-zero number, so we can write this is the we can take this is this, if f zeta minus fa is not equal to 0, so its modulus value, this is the f zeta minus fa, it should be a positive number, and we are writing this positive number by it is the by 2 of m. Okay, where this m should be greater than 0. Okay, now we need to prove this theorem. We need to now we need to prove that every W, if we take a point W, that is in a disk at center FA of radius m. W is a point in a disk of radius m at center FA is an interior point. Okay, so that we need to prove. Okay, so that is we need to prove, we need to show that W, this W, which is this W, which is a point in a disk of radius m at FA. So this W is in range, this is in range of F. Okay, so that we need to prove. Now for all, if we take for all, zeta is a number on C. Okay, this is not C, this is zeta, and that is on the circle C. We have this is the mode of f zeta minus W. So this I can write f zeta minus of f a, and this one plus of, that is the f of a minus of W. Now using triangle inequality, we can write this is a greater than equal f of zeta minus f of a, that modulus, and this is the minus f a minus W. Okay, so and this f zeta minus f a, we know that this f zeta minus f a is equal to 2m. So this is equal to 2m, and this f a minus W, that is the distance of f a by W. So by this one we can show that this is greater than, so overall this number is greater than m. Okay, so finally this is the value, this is equal to m, and we know that this m is greater than f a minus W. Okay, now if we rewrite, this is the we rewrite, if we rewrite last inequality. So we have, so if we rewrite, so we can write this is the f a minus W. So we are taking this f a minus W. So I can write it is the f of zeta minus W minus f of zeta minus of f of a. Okay, so this is this number as this mode of f a minus W, this is less than f zeta minus W. So this number is less than f zeta minus W. Okay, that is valid for all Z belongs to C. Okay, now we can see if we use the Rouche's theorem. Then the zeros of this f zeta minus W and f zeta minus Fa will be same inside C. That is, we can say that by Rouche's theorem, a function, this is the functions, that functions f zeta minus W, this function f zeta minus W and f zeta minus Fa, will have same number of zeros, that will have same number of zeros inside C. Okay, but we can see that this f zeta minus Fa is having at least one zero inside C. because this z is equal to a is 1 0 of f zeta minus f a, and there may be any other 0 also. So we can see that this f zeta we can write, but this f zeta minus of f a, this f zeta minus f a, that has at least 1 0 inside C. It means this f zeta minus w, that is the f zeta minus w, that will have at least this has at least 1 0 inside C. Okay, so if that 0, therefore we can say that there exists a z prime that we have said that f zeta minus w has at least 1 0 in C. It means there exists a z prime inside C, that is the disk delta at a of radius rho. Okay, so such that this is the f of z prime. This f of z prime, this is equal to w, because this f zeta minus w has at least 1 0. It means f of z prime minus w is equal to 0. It means this f of z prime is equal to w. Okay, if this one, so we are having that this w, this is in the range, this is in range of f. And if this w is in the range of f and this w is arbitrary, since this w is arbitrary, since this w is arbitrary, our result follows, that we can say that the result follows. Okay, that means we can show that every point w is an interior point, every point w in fd is an interior point, and if every point of fd will be an interior point, therefore this fd is an open set. Okay, so that was the proof of open mapping theorem. So that was the one thing. We can also see that in the open mapping theorem we have taken the open set. That means in the open mapping theorem we have taken that if f is a non-constant analytic function in an open set in D. Now we are interested to replace this open set by a domain. So that means we can say that we may have another result that if f be let f be non-constant analytic function, constant analytic function on a domain D. Okay, then fd, then this fd is a domain. Okay, that we need to prove. And to prove this one, we can see that we already proved that f, since f is a non-constant analytic function in a domain D, it means a domain that is this is open and connected set. So we already proved that fd is a open, because if f is a non-constant analytic function in an open set D, then fd is open. So we already proved that fd is a open set. So we need to prove only, that fd is connected. this FD is connected. Because we already proved that this FD is open. So we need to prove only that this FD is connected. Okay, now to prove this FD is connected, we can see that if let this is the D, which is a domain in Z plane, and let this is equal to the F of D. So if we take any 2 point, if we take one point W1 and another point W2 in FD, so since to prove this FD is connected, so we can see that these point W1 and W2 are the image of some point Z1 and Z2 in D. So therefore we can see that this W1 is just the F of Z1 and this W2 it is just the F of Z2. Okay, and since this D is a domain, that means D is connected. If D is connected, then these points Z1 and Z2 are connected. So if these points Z1 and Z2 are connected, so we can have a finite number of line segments. They are connecting Z1 and Z2. And since this F is analytic, so this F can map these line segments to the curve in FD. So all these curves that are connecting W1 and W2, they are smooth. Okay, and all these curves are connected. So this W1, we can connect W1 and W2 with finite number of curves. Okay, so therefore we can say that this FD is connected. Okay, so that was the proof of this one. So finally, we can give one more applications of open mapping theorem. So which is also a result for a univalent functions, that is the this result we are giving that if Fz, I am taking if Fz, if this Fz having the series representation, that is the Z plus it is n is equal to 2 to infinity, it is the a n of Zn. This one is such that the summations of n is equal to 2 to infinity, that is the n of a n, that is less than equal 1, then f, this function f that is having this series representation, then f is univalent. Here we mean by univalent is that this is the 1 1. Okay, this is univalent in the open unit disk. And that is the open unit disk. It is the delta. It is the Z such that mod of Z is less than 1. Okay. So we need to prove that if a function fz is having such a series representation with the conditions of its coefficient, that is the summations n is equal to 2 to infinity n of mod of an is less than equal 1, then such a function f is univalent. Okay. Now to prove this one, we can see that if I just take the proof is straightforward, and we can use Rouche's theorem to prove this theorem. So I just take let z naught is a point in delta. Okay, so if this z naught is a point in delta, then I am taking this is the f of z minus f of z naught, this one minus of z minus z naught, and we can write this is equal to n is equal to 2 to infinity, that is the a n of z of n minus z naught of n. Okay, And further we can write this one, that is the z minus z naught. We are taking a term out that z minus z naught. So this is the n is equal to 2 to infinity a n, and we are having this is the z of n minus 1 plus z of n minus 2 of z naught plus up to z naught of n minus 1. Okay. Also we have that as the modulus of z of n minus 1 plus z of n minus 2 of z naught plus that is up to z naught of n minus 1. So we can write using triangle inequality that mod of z n minus 1 plus mod of z n minus 2, that is the mod of z naught plus up to z naught of n minus 1. Okay, and since both z and z naught lie inside unit disk, it means this mod of z that is less than 1. So this number is also less than 1, this number is also less than 1. So finally this is less than 1. Okay, when z belongs to delta. Okay, if this is, so finally we are getting that that is the f of z minus f of z naught, this one minus of z minus z naught, this is the equal to z minus z naught, and this is the n. Okay, we need to take the modulus here. So we will have the modulus here, and that is the modulus here, that is n is equal to 2 to infinity, that is the mod of a n, and the modulus of this number will be less than n. So we will have this is the n of mod n, and since by hypothesis, okay, and but this is less than equal, and by hypothesis this number is less than equal 1. So we are getting this is the z minus z naught. Okay, this is not less than equal, this is completely less than. Okay, so finally we are getting this one. Now we can see by using Rouche's theorem that this function and this function will have same number of zeros inside unit disk. And since this z minus z naught, this is having only 1 zero inside unit disk, it means this fz minus fz naught, this will have only 1 zero inside delta. And if it is having only 1 zero, it means this f is 1 1. That f is 1. Okay, here we should take that this z naught is not equal to z. Okay, if this is, so we can prove, we can find a criteria of univalency by using the Rouche's theorem. So finally we are ending this lecture. Okay, thank you.